So I'll jump right into it. So I'll just give you a quick overview of what we do at Instaclustr. Instaclustr is a managed Cassandra and DataStax Enterprise in the cloud product. We basically offer a self-service dashboard that allows our customers to create and manage and monitor their clusters. And the whole point is it's sort of, as I said, self-service. So you can go in, twiddle a few dials, and then such as the size and the capacity and what provider you want your cluster to run on, and then you click the Go button, and we go off and provision it for you. It's pretty instantaneous. And then once it's up and running, we do all the monitoring and kind of behind the scenes maintenance operations and everything required to keep Cassandra running at top-notch performance. We have a free trial offered for developers, so I encourage you to go and have a look and play around with it if you got the chance. And I suppose, just a bit of history about how Instaclustr came about. It grew out of a need for using Cassandra in a project that Ben, the other co-founder, and myself were working on. We we wanted to focus on our project rather than having to manage Cassandra. And so we went out to the market and tried to find somebody who basically did what Instaclustr does, but couldn't find anybody that really sort of did it the way that we wanted. There was one service that existed, but they sort of ran Cassandra behind the sort of HTTP JSON API thing, which is very similar to AWS DynamoDB. So it's you don't get great performance out of that. So what we ended up doing, was we stopped the project and pretty much decided to work on Instaclustr instead. And so 2 years later, here we are. So today, what I'm going to talk about is how we use Docker and CoreOS at Instaclustr to basically make all this magic happen, how we use it to make sure that all your clusters that are hosted on us are always available, and all the maintenance operations and stuff that we do in the background are all seamless and pretty much invisible to our customers. So why did we pick CoreOS and Docker? Well, going back nearly 2 years ago now, we originally used to run on Ubuntu. And the way we did this, we started off on just Amazon Web Services, EC2. And initially, the way that we did it was we just ran a custom Ubuntu AMI, and this was just based on the stock Ubuntu AMI with a bunch of customizations, cloud and NetScript that raided the disks together and fetched the config from our server and all that sort of stuff. And the way Cassandra was installed was just, the traditional apt get install Cassandra, or if it was for DataStax deployment, DSE Cassandra. This has a number of problems, but we stuck with it for a long time. But those problems started to grow, and so we kind of started to investigate other solutions to kind of make our lives a lot easier, I suppose. So some of the issues that we were facing was, as I said, originally we started on Amazon Web Services, so these problems kind of grew out of that environment, but it turns out they're actually applicable to most cloud providers out there. On AWS, we use instant storage-backed AWS instances, and so instant storage is basically it's like an ephemeral disk that's attached to the instance. We use it because it's insanely fast. These days, it's all powered by solid-state drives. And you also get extremely low latency because the disk itself is attached kind of directly to the hypervisor, I suppose. I mean, they don't really go into the details about that, but you get extremely low latency. But the problem with these is that it's volatile, right? If you terminate the machine or or anything like that, the data on that disk is gone. The alternative to instant storage, which is elastic block storage, is Amazon's version of a network attached device or a SAN. It's slower, you get higher latency, And you also end up sharing bandwidth. Like you've kind of got one NIC on your instance that not only is Cassandra then sending data to and from clients and other nodes in the cluster, but then you're also reading and writing to EBS over the same network interface. So your instance is basically competing with itself to get bandwidth to write to disk. And so the only way that you can change machine images once you've booted an instance is to start a new machine. There's no way to kind of restart a machine into a new AMI. So that meant that it wasn't really possible to use this concept of using immutable images with persistent data on those instance storage drives, because as soon as you wanted to do upgrades of Cassandra or any of the other software on the machine, the whole immutability concept is kind of thrown out the window. So really the only feasible solution on a instance storage backed AWS instance was, when we were using Ubuntu, was to use just, apt-get install new versions of Cassandra and the other software on the machine. Obviously, replacing instances, it is a business as usual thing. Obviously if the node goes down or something like that, we have to handle instance replacement. But we didn't want to have to replace machine every time we wanted to upgrade software. So, it's not okay for upgrades because node replacement takes forever. You can only really do one node at a time, and so if it takes forever, you end up, if you want to upgrade the whole cluster to a new version of Cassandra, if you wanted to change machine images, it could take days for you to do a rolling restart. So the end result there is you end up with really painful and slow upgrades. So we went looking for a better solution, and that solution is CoreOS and Docker. So what is CoreOS? CoreOS is one of the first Docker operating systems. This is one of these operating systems basically designed for running containers. It doesn't have much of a user land. It's very small. It's minimalist. As I say there, it doesn't even have man pages installed in the default user land, which that has been a bit of a nightmare sometimes for support people. But anyway. It does have kind of this toolbox environment thing where, which is a container in itself that allows you to kind of do more maintenance operations and things. But because it's in a container, you're kind of limited to whatever a container allows you to do. So you can't really do things like mount new devices and do disk operations and all that sort of stuff. But all those kind of negatives aside, what CoreOS is great for is the fact that it runs Docker, and it's this nicely integrated environment. They've done all the testing to make sure it works really well. And it also comes with a bunch of other really useful software, etcd, Fleet, etc. As I say there, we don't currently use these internally ourselves, but we do have plans in the future to use things like etcd. etcd is a distributed key value store, similar to Zookeeper. It also supports distributed locking and stuff like that. And Fleet is basically a distributed service management framework. It sort of sits on top of systemd. CoreOS is well supported. It's in use by some of the big players in the market. Rackspace uses it, PlayStation uses it, we use it. Recent funding from Google Ventures was given to the CoreOS guys. And so it just kind of starts to validate the fact that it's becoming one of those names that, when you talk about Docker, people go, oh, well, are you using CoreOS as well to run your containers? One of the other features of CoreOS that we found was quite useful when we were sort of looking for it, and it just ticked another box, I guess, was when we were doing the port to GCP, which is Google's cloud, they didn't have Ubuntu images. They weren't building those, so we were going to have to build Ubuntu images ourselves, whereas CoreOS was available on GCP, is available on GCP. So, it meant one less thing for us to have to manage ourselves. And the greatest thing about CoreOS, besides the fact that it uses Docker, is also that it runs systemd, which, these days I think Ubuntu runs systemd as well, but at the time they were running Upstart, which we had a few issues with. And it also runs dbus as well, and I'll go into a little bit on systemd and dbus a little bit later. CoreOS themselves, so they're responsible for building the images that we run on, so the AMIs for Azure, AWS, GCP, etc. So that means there's one less step in our build process. And one of the great things about CoreOS is it's got this concept of in-place updates and rollbacks on failure, which, and the way that works is they sort of have two system partitions. One is active at any particular time, and the other is inactive. And then when it wants to download and install updates, those updates are installed to the inactive partition, then swaps the active flags around, restarts the machine, and you're now running an updated version of the OS. But if something goes wrong in that update process, you can roll back the update by just swapping those active flags back around, and you're sort of back to the state you're on. All your data itself is stored on a separate partition, so that data includes things like configuration, your Docker containers, images, all that sort of stuff. So that's all persistent. But the thing about this is it gets around the problem of doing immutable sort of images where, CoreOS are the guys that manage the in-place update procedure. We don't have to worry about that. So the system updates, kernel, all your core library components and everything, all those updates and that process is all vetted by CoreOS. We don't have to worry about ourselves. The only thing we worry about is doing the Docker container stuff. So Docker. What is Docker? Well, it's a container runtime, and a container is kind of like a lightweight virtual machine. It's also a standardized image distribution and hosting kind of environment, and there's a whole ecosystem around all this stuff, right? So, there's kind of, not only is there's the kind of core Docker group, but then there's other people like key.io, which we use, that they do like private image hosting. So this whole ecosystem is starting to grow around Docker, which makes it really great to get started. There's a lot of community involvement, which is fantastic. When we bring new developers on board, they can they can sort of, there's a lot of documentation stuff out there already that they can go off and read. So it's kind of well-used tech, and it's starting to get a lot of traction. You start to hear about people using it in production. I gave a presentation at the beginning of the year, and a few people were like, oh, you use Docker and CoreOS in production, but we've now heard about a couple of other people that use it, so glad we're not the only ones now that are using both of those things in anger. But what Docker basically gives us is the immutable images component, right? We can, we create a new image, and then we run it on the machine, and then when we want to upgrade to a new image, the old container is thrown away and a new container is created. So basically lets us reset to kind of that known good state. There's no cruft that builds up. The only thing that we keep around is the Cassandra data and the configuration and stuff like that. All the libraries and all the components about Cassandra, they're uninstalled or destroyed, or whatever you want to call it, and redeployed every time we want to upgrade Cassandra. The Docker images that we deploy, like we build them in our development environment, those same dev images get kind of moved over to our testing environment once development has been completed on a feature or something, and then once testing is completed, those exact same images are pushed to our production environment. So we have this nice flow through where a thing is built once or multiple times in dev, obviously, but then pushed once into test and then pushed from test into production, meaning that we're certain that what we're pushing into production for our customers is is kind of, you know, we've tested it, we've vetted it. And, you know, the whole thing with immutable images, right, is that it means that software installs and uninstalls everything are all clean. So, and it allows us to do isolation of existing components. So, you know, we've got a few things where, like, our tooling runs OpenJDK. Cassandra really requires Oracle JDK. So, you know, trying to install both on a traditional system without containers would be painful. I mean, you can do it if you want to, but it's more complex. The packages and stuff don't really support it. Whereas because containers are completely isolated from each other, you know, we can have all these different library versions, different JVMs, etc., and they can all coexist on the one machine. And not that we use it, but it even lets you run kind of different user land layouts. So, you know, if you're more preferable for CentOS versus Debian or something, you know, the packages and things for those different distributions can be used inside containers. So combining the two together, like I said, Docker basically gives us that immutable images for our components without having to do the instance replacement. And then CoreOS handles the rest. So all the kernel upgrades, OS level libraries, everything, we leave it to them. Docker is completely provider agnostic. It runs on Linux. That doesn't matter about the provider. And then CoreOS runs on every major cloud provider that we want to support, and also on bare metal. So we've, I think it's in beta, started supporting IBM SoftLayer, and SoftLayer does bare metal deployments. And, you know, so, you know, CoreOS just runs there like any other operating system, which is fantastic. So it basically means that Instaclustr managed Cassandra can run anywhere. You know, we want to onboard a new cloud provider because we've got demand from customers. It's quite easy for us to do so. And the combination of Docker and CoreOS makes this a lot easier. So the integration, so how we integrate Docker and CoreOS into our environment, the main thing, of course, is Cassandra itself. So the Cassandra data and configuration is persistent on the host, which allows us to restart containers, upgrade it to a new version, something like that. And the way that this is done is that the Cassandra data directories and configuration, like etc Cassandra basically, is mounted from a directory on the host. So that data is then persistent. And kind of, you know, I guess the way you can look at it is we've sort of put another layer on top of Amazon Web Services or the cloud provider, where, you know, originally we were storing data on their ephemeral disk, and we've got this operating system, and there's no way to replace the operating system without losing any data on the disk. Whereas by putting a layer in between, we can replace that in-between layer, the container, without having to restart the operating system, but the data is still persistent on the ephemeral drive. And this, because it works so well, we actually containerize everything. Not just Cassandra, but all our internal services, the stuff that runs on our central services to do our console, website, databases, all that sort of stuff, Cassandra that we use internally for logs and monitoring, all the node management tools, all that sort of stuff. It's all done through Docker containers. And because most of our applications are, like our internal apps are Java-based as well, Cassandra's Java, of course, it allows us to use this single kind of, it's a well-understood build process. Makes it easier for our devs. You know, again, if we want to bring somebody new on board, basically say to them, look, the way everything is built is exactly the same. You know, you don't have to figure out how Cassandra is built versus our internal tooling. It's exactly the same thing. And so we basically wrap Docker build and Docker push in a makefile. The makefile does, you know, a few fancy things like fetching dependencies and stuff to install into the image. But then, you know, if you want to build everything, you just go make, and voila, you've got Docker containers. So I'm just looking at my notes here. So one of the nice things that Docker lets you do is it has this concept of image inheritance, which is basically one image can sort of depend on another, which allows you to kind of isolate and consolidate common components, tools and utilities and libraries and all that sort of stuff that are used by a lot of images. So in this diagram here, this is kind of like a general layout of how we build our images. You'll see that, we base everything on Debian. We then have this common base image which contains things like OpenSSL, Python, curl, kind of all those common utility libraries that are useful everywhere. And then we've kind of got a JDK container for each of the distributions, OpenJDK and Oracle. And then on the Oracle one, we've got like a Cassandra common thing, which includes a few sort of config extra libraries and whatever that are used by both DC and Apache. And then we've got a container that, image that contains Cassandra from the Apache project and Cassandra from DataStax. And then we could selectively deploy whichever one our customers ask for. We also use Docker containers to containerize OpsCenter. So we let our customers access OpsCenter through our dashboard. So there's a button, Launch OpsCenter. And the way that this works is we deploy one instance of OpsCenter per cluster that we deploy. We do that for a bunch of reasons, mostly for security purposes. OpsCenter itself doesn't really have tight security controls, especially the community version, which is what we deploy. It's also hosted independently of the cluster on a separate machine, and that kind of gives us the benefits of, independence from the cluster by itself. And, so if the cluster undergoes a restart, OpsCenter keeps on running and so on. One instance of OpsCenter is equivalent to one Docker container. So we've got a host that is running lots of Docker containers, or actually it's on multiple hosts for redundancy, but a bunch of Docker containers, one OpsCenter per container. And the main reason why we chose this method rather than launching like a separate EC2 instance for every OpsCenter instance we want to deploy is that it's extremely cost effective. We can run, a couple of hundred OpsCenter instances per machine versus one instance per EC2 instance, the traditional method. But getting back to the main reason why we use Docker and CoreOS is to handle Cassandra versioning. So like I was talking about previously, we had this problem of how do we upgrade existing nodes to a new version of Cassandra without doing apt-get. The reason why we want to do this is, obviously upgrades is the main thing, but we also want to support multiple versions of Cassandra for our customers. Some of you guys have got, requirements that you run 2.0 for stability. Other people want to use 2.1 for the new hotness. We also, give customers the option to deploy the Apache version or the DataStax Enterprise version. And it allows us to also, roll back when, a new version is deployed, and even though we've tested it and people are using it, there might be a bug discovered by somebody in the project. And so, we can roll back to a previous version of Cassandra with ease, whereas trying to do rollbacks through apt-get is actually quite painful, if things don't quite all align properly. So what we do is we have one Docker image per Cassandra distribution. So we've got like an Apache Cassandra image and a DataStax Enterprise image. And then we have one tag per version of that image. So we can then launch a particular container with an image for the version that the customer's requested. The other thing it does is that it reduces the number of images that we actually have to manage. Like the old traditional way of creating Ubuntu AMIs with each version of Cassandra baked into it was that AWS has this kind of a little bit of a crazy limitation really, but it's just the way that it works, where you have to create an AMI per region. So while you can copy the AMI to each region. You've got to register it with your API and all that sort of stuff. And so, as a result, AWS has 9 regions. We support all of them. And therefore, every version of Cassandra that we support, you'd end up with 9 images. And because we currently support 2 distributions, and at last count we had total like 13 versions, like some customers haven't upgraded, things like that. We've got a few in beta. Across 3 different cloud providers, in total with all of those guys, they've got like 29 regions all up. If you do the math, it turns out to be approximately 377 images, and that number is just going to grow over time. Whereas with Docker, you end up with 1 image per version, and that works everywhere, which is fantastic. It's kind of the database structure and everything that we had to have previously to support the different region versions and all that sort of stuff was quite complicated. Whereas now it's just oh, you want version 2.1.10. Launch it, here's the image ID to run, and you're done, basically. It's nice and simple. The way we handle versioning at Instaclustr is every cluster that we launch has a specific Cassandra version associated with it. This version is selected by the users at creation time. We have a curated list, so it's typically the current and current -1 for each distribution. And we sometimes will also give customers access to beta versions if they've asked for it. But the advantage of having every cluster with a kind of a known version associated with it is that when if a customer asks to add new nodes or we have to replace a node because it's failed or something, that node will launch with exactly the same version of Cassandra. Whereas, if you're not careful and you just do apt-get install Cassandra without pinning the package to a known version, you're going to get slightly different point release versions running around your cluster. And one of the fantastic things is that the Apache software Debian package repository is that they only keep the latest version of Cassandra around for each each branch, I guess, 2.0 or 2.1. And so it means that if you want to actually go back in time, if you want to run like a previous version, you've got to download it off their other mirror, which isn't actually a Debian repository. And so you've got to kind of manually install the package, which has got a whole bunch of pain points and stuff. So it was kind of, that was yet just another thing where we went, we need to be able to keep these versions around ourselves rather than kind of relying on the remote package repositories to contain all the versions we want to run. And the end result is that like every cluster that we're running has a known, sane configuration. Every node's running the same version of Cassandra, and we can handle upgrades and all that sort of processes, elegantly. So how do we roll out upgrades? The process itself is actually quite simple, and we're kind of, it's the same each time, and unless something goes wrong, we can actually do this quite quickly. So it allows us to be very reactive to like the Apache project producing new versions of Cassandra, because they fix bugs quite frequently, which is nice. So the procedure that we do is, we build a new Docker image for the Cassandra version that's been released, and like development and stuff continues on that. And then we deploy that to our testing environment, and we do clean installs of that version and also rolling upgrades of test clusters running previous versions as well to verify that the whole upgrade procedure works reliably. And we then enable those images in our production environments to select customers if they've asked for it, or to our internal support teams to do a bit of field testing, just to make sure that there's no. We try not to have differences between test and production, but unless something might have slipped through the cracks, so we just want to do a bit of testing in prod before we say it's generally available. Then we make it available to everybody. This typically means that new clusters that are launched will run the new version of Cassandra by default. We typically allow people to choose the previous version as well, just in case they don't want to be running the bleeding edge. but it sort of means that everybody's always launching new clusters with the latest version. And then for our existing customers, we liaise with them to kind of determine the best time and strategy to do a rolling cluster-wide upgrade. This is pretty painless. You restart each node one at a time, waiting for it to rejoin the ring. Standard Cassandra procedure. But because we're basically just changing images, swapping one out for another, the process is actually quite quick. The node just has to download the new Docker image and restart, and you're back up and running. So it's quite painless and very, very simple. So just to give you a visual diagram of what we've kind of managed to accomplish here is, you can imagine a node, and so on the left-hand side, we've got Docker containers, and on the right-hand side, we've got AMIs and then apt get install upgrades. So you can see on the right-hand side, what happens is we build an AMI for 2.0.10, and somebody launches a cluster with that AMI. And then forever onwards, what we have to do is apt get install every new version on top of that, unless we want to replace the node. And then when a new version of Cassandra comes out, we build another AMI, 2.0.11. But then the same thing happens. Every version that's released afterwards, you have to apt get install on top of it. So you end up with these kind of images that slowly diverge off the kind of main line, and that are forever slightly different from everything else. Whereas in the Docker case, every image, you just kind of replace it with the next one as you go along. So you get that nice clean state every time. So there's no cruft build-up. We're kind of, almost certain that it's going to work reliably every single time we want to do this, which is, just another thing that allows us to do, it simplifies operations. Sorry, this is more like a textual description as well. So a case we had was we're trying to upgrade. I think the version numbers of the Cassandra packages here are wrong, but an example was, we tried to install Cassandra, like a newer version on the node, and that package changed a few things around how they sort of, bundled things up, and it didn't quite correctly, it would uninstall things from just the previous version, but if you were doing a larger upgrade, so if you went from 2.0.10 to 2.14 in this case, we ended up with like a few things that weren't quite right, like Cassandra itself wouldn't start up, and so you're then there on the node deleting files and editing files and figuring out why it's not working. Whereas the Docker case, you just launch the new image, and because you guaranteed that clean slate every single time, it just works. So you can go out and party afterwards rather than being all upset and sad. And in the case of rollback, the same thing happens. If you install the new package and Cassandra doesn't want to start, you got to run a bunch of commands. The first time I didn't know how to do this, I had to go off and Google it, and you hope that the remove and the purge and all that sort of stuff fixes the problem, and then you try and reinstall the old version. And as I said, because they don't keep the packages on the repository, you can't just install 2.0.9 anymore. You're going to go off and fetch it from some other mirror, download the deb, and then manually install that plus all the dependencies. Whereas with Docker, you can just install the old image and you're back to where you were. Nice and simple, nice and clean. So onto a little bit more of a sort of technical side of things. So CoreOS has or uses a service management system called systemd, which is a sort of, what would you call it, a modern replacement for systemd init and upstart and a whole bunch of these other sort of service management frameworks. pretty much does the same thing. It's got a few nice things about it. I know there's a lot of hate on the internet for it as well, but for what we needed to do, it does it really well, so we're quite happy with using it. It supports inter-service dependencies, as any service management framework should. And so, an example of that is, we have a service that runs on every node that takes automatic snapshots periodically and uploads those to a backup service. And that snapshot service requires Cassandra. And, because it needs Cassandra to be running in order for it to ask Cassandra to take a snapshot. And, so we've kind of got this dependency that says, only run snapshot service when Cassandra is available. Systemd does all the automatic restarts. So we've kind of designed all our internal services, so the backups, monitoring, all that sort of thing, to be fail fast, i.e. if they encounter an error condition, we just bail out. We don't try and recover from the situation and let Systemd restart us, which simplifies a lot of things. Cassandra, there's a few cases where it kind of can get itself into a bit of a bind. A lot of these have been fixed over time, but we've seen issues where there'll be like a thread pool or something inside the application that's starved for resources, and the only thing is to actually manually restart the application. So, but Systemd kind of handles all this automatic restart for us. The other component that we use in combination with Systemd is dbus, which is pretty much just a remote procedure call between applications. It also does kind of notifications between apps as well, so when things have changed in one application, another application can be notified when that happens. It's all socket based, and one cool thing is that it has like multiple language bindings. So not only is there a C library, but there's a dbus library for Python, there's a dbus library for Java. So what we can basically do is we can control Systemd via dbus through Java, so you don't have to fork and exec system control or something like that. You can just call dbus directly. And because it's all socket-based, you can actually mount the socket into a Docker container, and then you can control the host Systemd inside a Docker container. So we don't actually have any management tooling running on the host, except for Systemd, because that's like a core system component. The management tooling runs inside a Docker container and then controls the host via dbus. And just to give you an example of what you can do with like dbus Java is, system control restart Cassandra basically becomes, Systemd manager.restart unit. And so it sort of allows you to integrate quite well with Java applications and things, and it'll throw exceptions if things don't work and so on. Whereas trying to handle command line input and output and parsing results and stuff is kind of that all disappears by just using the wrapper stuff, which makes our lives quite a bit simpler. And so one of the things we've been working on is trying to more tightly integrate Cassandra with Systemd and dbus. And the reason for that is like Systemd kind of has this concept of like a service status, whether or not it's starting or stopping, or if it's active or inactive. But the definition of that can vary. Does active just define that a process is running? Does the PID exist, or does it actually mean something more? So in the Cassandra case, does it just mean that Java is running, or does it mean that Cassandra is actually accepting SQL connections? And the reason why I kind of asked this question is because Systemd will start dependencies when the required units become active. So going back to the snapshot service example, the snapshot service will start as soon as the Cassandra service becomes available. But if the snapshot service was to require, say, CQL, so SQL clients are dependencies on Cassandra, right? they shouldn't start until CQL becomes available in Cassandra. Like when Cassandra starts up, it doesn't actually start listening on the CQL connection port straight away. There's a whole bootstrap process that has to happen before that socket is opened. And if it's a node that's actually joining an existing cluster, it actually has to stream all the data from all the existing nodes in the cluster first before CQL connections are accepted. And so that process can take hours. So you end up in this situation where systemd says Cassandra is active, all the dependent units start, but then they try and connect to Cassandra and it goes, no, you can't do that. So, obviously you've got some options in your clients where you could, those like smaller clients that just want to do one thing, they could fail fast and just, wait for systemd to continuously restart them. But if you've got larger, more complex applications that are trying to, do a lot of stuff, they often will require sort of like a reconnect loop. You're managing the Cassandra connection. Can I connect? Oh, no, I can't. Back off, try again in a second. So what we wanted to try and do is figure out how to get Cassandra to integrate more tightly with systemd so that these dependent units would only start when CQL becomes available. It simplifies a lot of our tooling on the nodes if we can accomplish that. So one option, and this is the simplest option, is systemd allows you to notify it when a unit actually becomes active. So the default out-of-the-box behavior is, oh, the process that I've started exists in the process table, therefore the unit is active. But you can change that default to something where the process has to notify systemd when it starts. And so what we've managed to do is we've written a Java agent that what it does internally is continuously tries to attempt the connection to the CQL port. So Cassandra is sort of trying to connect to itself here. But as soon as it manages to establish a connection to CQL, then we notify systemd that Cassandra is actually now active. We use a Java agent for this. So a Java agent is it's kind of like a sidecar component that you can load into the JVM. It's typically used for like debugging purposes and stuff like that, but an agent actually has full access to everything that's running inside the JVM. So you can do things like open sockets and run threads and all that sort of stuff. And the reason why we did that is because it means that there's no code modification. Like, sure, the Apache project is open source, so we could have gone in and changed the main class or something like that to actually have this background loop to attempt the CQL connection. But we can't modify DataStax Enterprise, and because we support both on our platform, we needed a thing that works for both. So using a Java agent means that the same agent works for the Apache project and DataStax Enterprise, and it doesn't require any code modifications either. The only disadvantage of this is that the unit will stay in activating, I think that's the state, for a, depending on how long Cassandra takes before it allows CQL connections, it can take quite a long time. Like, we've seen it take many hours if a node is trying to join a ring. So you have to actually set, there's a timeout value in systemd, which I think defaults to 10 seconds or something, where if systemd doesn't receive notification from the process after 10 seconds, it just nukes it. You have to set that to 0, which is disable it. Otherwise, if it takes hours to do this notification, systemd will just kill the process. I did mention, sorry, just going back one slide here, where one thing that Cassandra is, though, is that it is more than just CQL. There's Thrift connectivity and there's JMX as well. So JMX is quite useful for a lot of monitoring and maintenance operations. And Thrift is, like, we don't use it, but of course it's the more classic connectivity mechanism. And if we wanted to open source this, we'd probably want a solution that works for all these kind of connectivity options for Cassandra, not just CQL. So unfortunately, the agent stuff, because it's just a notification to say that, you can only say that the unit has started or stopped. There's no kind of it is now accepting a connections on a particular socket or something to systemd. You need to have some kind of alternate mechanism for this. So the other thing that we've been playing around with, so this actually hasn't been like we've tested it in dev, but we're not actually using it in production, is you kind of have a simple service, systemd service, like in this example here, Cassandra CQL, which is inserted into the dependency chain between the client application that wants to use CQL and Cassandra itself. And the Cassandra CQL service is just, it's like a wrapper around a very simple tool, it could be a Python script or something, that watches a port for connectivity. So it's basically doing the same thing as what that Java agent was doing, attempting a connection to the port, and if it succeeds, marking itself as successful. But if the connection fails, exit the process, and therefore the dependent application, in this case the client, won't start because the kind of parent dependency fails to start as well. So systemd handles this. And you can have multiple versions of this simple service. So you could have one for thrift, and you could have one for JMX connectivity. And if Cassandra was to introduce any other kind of connectivity options in the future, you could sort of expand this out a little bit more. So in the long run, this kind of does seem to be the more graceful option, I think, and we've had a bit of success in our development environments using this as a thing. So, well, I guess that almost wraps it up. So I think what we'll do is we'll open it to questions and answers. So, anyone got any questions?
Now's the right time to go ahead and type in those questions. So we'll go ahead and ask you one that's already been typed in. How do you deal with CoreOS reboots for updates, as in prevent data from getting rearranged if a node goes down for an update, since it will or / should be back within 2 minutes?
So as in prevent data from getting rearranged if a node goes down. So are we talking about whether or not Cassandra rearranges data there or something like that? So when CoreOS does a reboot for an update, it does that, swap the system partition around, but that doesn't affect any of the data on the node. So the data itself stays there on that well, it's called the data partition on CoreOS. And when Cassandra, or when the OS restarts into the new update, the Docker container for Cassandra will automatically restart, and Cassandra will just handle the resynchronization process with the rest of the cluster. It's like if you just turn off Cassandra on a single node for a couple of minutes. It's basically the standard operating procedure for doing Cassandra restarts. And we do a rolling restart around the cluster, so we don't restart all the nodes at once. We actually use distributed locking to prevent that, so our support people can't hit the restart button on every node at once, which basically means, we wait for each node to restart and rejoin the ring before restarting the next one. Does that answer your question?
I think so. Here's another one. Is it beneficial to embed Cassandra instance in a Docker image, so when a Docker spun up, Cassandra starts with it? We actually build a Docker image with Cassandra embedded in it or baked into it. So as part of our Docker build, the Docker file, there is actually a apt-get install line in that Docker file to embed Cassandra inside in the container, or sorry, the image for the container, and all its dependencies. So Java, any utilities and libraries that it depends on are also installed as well.
So I'll just go back to the slide where I gave the sort of layout. Where is that? So this here. So you see that, like, you know, we have an image for Apache Cassandra down the bottom on the left there, and it depends on a common image, which depends on the Oracle JDK image, which depends on a base image, and so on. And so because Cassandra, like, we're running a single application per container, yeah, when you start the Docker container, Cassandra automatically starts with it. We don't run SSH or any other components inside a Docker container. We use it for the, I guess it's the recommended approach, where it's kind of one primary process per container. Like, we don't even run syslog or anything like that in things. Like, Cassandra is running as PID1 inside the container that we run. Does that answer your question?
Here's the next question. What happens with data when you roll back?
So I guess that's rolling back Cassandra versions. Well, because the data's, we mount a directory from the host, so the host being CoreOS in this case, into the Cassandra container that we're running. And when we want to do a rollback, we basically replace the container with a different one, just running a different version of Cassandra, and you know, Cassandra handles the rest. So the data formats are compatible between minor point releases, so you can go back one if it fails.
How do you deal with changes in Cassandra YAML while a cluster is running?
That's a good question. So we sort of have our own config management process, and actually I saw a couple other people asking about config management here as well. So I guess I'll just give a little bit of a quick kind of run through. So I don't have any diagrams or anything to explain this, but we let our customers customize a few Cassandra YAML parameters. You know, actually I can't think of anything off the top of my head, but you know, there's a bunch of them, and we then also generate a number of things such as the seed node list and stuff for the rest of the cluster. And so we have management software that runs on a node that we've written ourselves, and that management software talks to our set of central servers and requests configuration, including the Cassandra YAML. And it basically just downloads a tar file with all those files generated automatically. That tar file is then expanded into a directory on the host. You know, I think it's varlib instaclustr etc Cassandra, and that directory is then mounted into the Docker container under etc Cassandra, and therefore the generated YAML file that we produce on our server is then available to Cassandra inside the container. If a customer wants to change any of their configuration parameters, currently it's a support request. We are working on this. It's one of those things where they make changes to the configuration parameters, and those then update our central databases. And then the eventual thinking is that it will cause a rolling restart of the cluster, and the act of restarting the cluster will fetch a new Cassandra YAML from our central servers. So, you know, we kind of allow people to, or, you know, that's the current thinking. Whereas at the moment, as I said, it's a support request. So what support will do is do the rolling restart in place of an automatic procedure.
Great. We have time for a few more questions. Here's one. Have you had to deal with making any special modifications to the Docker bridge or network performance issues with the Docker bridge?
Where's that one? The Docker bridge or network. So we're actually running at least on the nodes, I think all our central services use like Docker's bridged networking stuff. But on a node itself, sorry, that was me, we run everything using host networking. There's a number of reasons for that. Yeah, one is performance. The other is because Cassandra, what is it? So because like when you run a Docker container with NAT-based networking, you end up with like an internal IP address. If you then run that on AWS, you end up like a node ends up with sort of 3 IP addresses. There's the public IP address of the node, the private IP address of the AWS instance, and then there is the private IP address of the Docker container. And like we tried to get Cassandra to advertise the right addresses and so on, but we ended up just giving up and said, you know, screw it, we'll just use host-based networking, because then the private IP address of the Docker container is just the private IP address of the AWS instance. Because we're not trying to run more than one instance of Cassandra on a machine at a time, this doesn't pose a problem for us.
How do you code Cassandra feeds? Do you allow your client applications to connect to all Cassandra nodes?
So seed nodes are determined when we launch instances. So our instance launch process is, you know, we ask, say, Amazon to start a machine of a particular size, and the act of starting the machine is allocated an IP address, and then we record those IP addresses. And then when each node attempts to fetch its YAML file and all the other configuration, we then return a select list of those IP addresses to each machine. Client applications are able to connect to every node in the cluster. Connectivity options, there's a bunch of them. One is you can connect via the public IP address across the internet. We support Cassandra's SSL encryption and password authentication to make all that quite secure. And then we also do firewall whitelisting as well to restrict it to just a set of application or addresses for your application. But if you're also running on AWS, we support VPC peering. So everything's all done via all like private networking and stuff. So it's all quite secure. So I hope that answers that question.
All right, here's the last question. Is Cassandra data forward and backwards compatible between point releases? Is it safe to skip releases?
So, like my understanding of it, the best person to probably ask that for us internally is Ben Bromhead, the other co-founder, because he's more of our super Cassandra expert. I'm more of the Docker and CoreOS guy. But my understanding of it is that to go between major releases, so 2.0 to 2.1, is compatible, but between kind of the last version of the minor version bump to the next version. So, you know, you can go from like 2.0.14 or whatever the latest one is to 2.1.5 without any pain. But on a minor, or sorry, what is it, the last, so the patch version, you can go up and down without any major changes, because they don't change the data, like the SS table formats, between patch versions.
Okay, great. That's all the time we have for all the questions that we didn't get to. We'll try to answer those to you shortly, and thank you for everybody attending. I hope you have a good rest of the day.
Thanks, everyone.